Greetings. So, we are now coming to a very interesting part of light atom interactions, which is the Jaynes-Cummings model. Now, Jaynes was a student of Wigner and Cummings was his student. So, this is a very famous model in light atom interactions, light matter studies or laser atom studies and so on. And I am going to depend heavily on this article, which is a tutorial article by Bina, which came out in 2012. That is going to be my primary source, although I would have used some other references, which I will of course be sharing with you. And this model was proposed by Jaynes and Cummings in 1963 and is a very big step in cavity quantum electrodynamics, okay? Both microwave cavities and also in the optical range of the electromagnetic radiation. So, the semi-classical model that we have discussed earlier, we described the Rebbe flopping and so on, but it required the presence of the electromagnetic field. And what the Jaynes-Cummings model will account for, which the semi-classical model does not account for, is the revival of the atomic populations, because in the absence of these, I mentioned in our previous class that the oscillations will die out and they will collapse, okay? Whereas the quantum nature of the electromagnetic field, which is addressed in the Jaynes-Cummings model, you take into consideration the discrete states of the electromagnetic field in terms of the photons, and they will also account for the revival of the Rebbe oscillations. So, this is the quantization of the electromagnetic field described in terms of the harmonic oscillator operators, all right. And you can also refer to this article by Shore and Knight, which I had mentioned earlier. So, basically you have a two-level atomic system interacting with one single radiation mode, okay. So, if you have atoms in free space, you have a number of different modes which are possible. When you have cavity electrodynamics, the electromagnetic field is confined to a particular cavity, then the standing waves will automatically pick only certain modes which can survive in that. And this is the same type of principle which is involved in Fabry-Perot interferometry, okay. So, you have got a certain light of wavelength lambda, and depending on the length of the cavity, means as I mentioned, one of these mirrors is fully reflective, the other one is partially reflective, and a certain amount of light can be extracted from this. The amount of transmission is given by this expression. So, these results come from usual considerations of optics as to how much energy can be extracted from this cavity, and these formulae can be found in usual books on optics. The mirror positions are adjustable, they can be very finely tuned, and you can get this transmission which you can determine, and in resonant modes you can find the corresponding amount of transmission which is possible depending on the reflectivity of the two mirrors R1 and R2, okay. So, what is the Jaynes-Cummings model? So, you have got a two-level system interacting with one radiation mode, okay. So, you have got a ground state and an excited state. So, this is the zero of the energy, and the ground state you describe it as minus half h cross omega and this as plus h cross omega. On the Hamiltonian, which is going to be the second quantized Hamiltonian, now not the semi-classical Hamiltonian that we have used earlier when we talked about the Rebai flopping. So, the second quantized Hamiltonian will consist of the second quantized Hamiltonian for the atom, then for the field, and then for the atom field interaction, which is HAF, AF for atom field interaction. So, it will consist of these three parts in the Jaynes-Cummings model, and the atomic Hamiltonian can be written in terms of these operators, because this is a two-level system, there is nothing else. Okay, so, there is only the excited state and the ground state, and the Ket-Bra operator, the difference between the Ket-Bra for the excited state and the ground state describes the atomic Hamiltonian, as you can see very easily, because when this Hamiltonian operates on the excited state is orthogonal to the ground state. So, this term will give you 0 and over here it will give you 1, giving you an eigenvalue equation with energy h cross omega by 2, right. And when it operates on the ground state, you have again this state gives you a factor of 1 through the scalar product, and with the excited state it gives you 0 because it is orthogonal to that, but you have got a minus sign over here. So, you have got a minus half h cross omega over here. So, the difference, this minus this, will give you the h cross omega. Okay. So, this is the atomic Hamiltonian, and this particular operator is called as the inversion operator, okay, for obvious reasons. So, now you can write this full Hamiltonian in terms of this inversion operator, which is the atomic Hamiltonian here. Then you have got the photon field, which is described by in terms of the creation and destruction operator for the single mode creation and destruction operator, F dagger creation and F annihilation operator. And then you have got the atom field interaction, which is something that we have to work with, we have to construct that. And as I mentioned in the previous class also, there is a complete mathematical equivalence between the spin half system and the two-level atom system. The mathematics is exactly the same, and you can see that this is a very similar situation. You have got the two-level system, you have got the atom in the ground state with n plus 1 photons, and an atom in the excited state. How does it get excited? By absorbing 1 photon. So, the number of photons has gone down from n plus 1 to n. Okay? N can even be 0. So, you can have a G1 going to E0, right, and vice versa. And this system is completely identical to the spin half system, whether it is electron or proton in a magnetic field. So, in this case the basis states are either plus half and minus half, or you can write them equivalently as states E and G, right, and you can even write them as states 1 and 0 if you like, right. These are orthogonal states, and the angular momentum algebra of the spin half states can be directly employed to do the mathematics of the two-level atoms, because the system is completely equivalent, and the spin half system is described by the Pauli matrices, the sigma x, sigma y and sigma z, corresponding to the angular momentum half, all right. So, sigma are the Pauli matrices, and you have got the raising and the lowering operators, the Pauli raising and the lowering operators, which are sigma plus and sigma minus, and then you have got this inversion operator type of sigma z, right. And accordingly, you have this inversion operator for the atomic two-level system between excited state and the ground state, and corresponding to the sigma plus and sigma minus, you have got the R plus and R minus, which are given by exactly the same matrices. The matrix representation is exactly the same, although you are not referring to the spin-off system, you are referring to the two-level atomic system, but it is exactly the same mathematics, and you see that there is a one-to-one correspondence between these operators. So, this is what you have got. You can also, you will be reminded of the qubit, because there again you have got two states, which is 0 and 1. These are the antipodes on the Bloch sphere, right, and you have got an exactly similar type of situation. It is again a two-level system, and you can carry out this analysis in terms of the spin half systems or the excited and the ground state states of the atom, or in terms of the qubit systems 1 and 0 states. Okay? So, this is the Bloch sphere that you will be reminded of, which we discussed in the previous unit of this course. Okay, so in the semi-classical description, you had the interaction represented by d dot E, okay, and it is then proportional to the dipole moment and the strength of the electric field. Okay, that is the strength of the interaction. Now, we are going to quantize this, and we have seen that the electric field per photon, which we discussed in the previous class, you can increase it by reducing the volume of the cavity, okay, and that energy, because the expectation value of the square of the electric intensity turns out to be the square of this quantity h cross omega over twice epsilon 0 b root, right. So, the electric intensity is now given by this 1 over v factor with which comes under the square root h cross omega twice epsilon 0 v, and when you quantize this atom field term, because we have these three terms in the Hamiltonian, the atomic Hamiltonian, the field Hamiltonian, and the atom field interaction Hamiltonian. So, the atom Hamiltonian we have already written in terms of the Pauli operators or the Pauli-like operators, okay, the raising and the lowering operators. The field operators we have written in terms of the photon destruction and creation operator, and we are now constructing the interaction, the atom field interaction. So, we have to quantize this interaction, the semi-classical interaction V prime is now to be written in terms of the second quantized operators. So, we are in the process of doing that. We have a single mode Rebai frequency, and we get it by making V small, right. The Rebai frequency, we define this xi so that omega r by 2 is equal to xi, and you can write this V prime in terms of the Rebai frequency, which is h cross xi, okay. And now what we need is to write appropriate operators to represent the transitions from the excited state of an atom with n number of photons, n can be 0 or more, to the ground state with an extra photon, which will be n plus 1. Okay? So, you can have a ground state with n plus 1 photons, 1 photon gets absorbed, you go to the excited state with 1 photon less. So, that will be E comma n, or the reverse transition, which will take you from E n to G n plus 1. So, what are you doing? You are raising the atomic system from ground to G. In the reverse process, you are lowering the state of the system from E to G, right. That is what you are doing to the atom. What are you doing to the field? In one case, you have destroyed a photon, you have absorbed the photon. So, you have destroyed, you have annihilated a photon, and when you go from the excited state to the lower state, you have created a photon. So your interaction is now going to be represented in terms of these lowering and raising operators for the atom and in terms of the creation and destruction operators for the photons. So let us do it now. So these are the raising and the lowering operators that we have seen, and these are the creation and the destruction operators for the photon, right? You have them in front of you. And in terms of these, you can now write the quantum description of the interaction between the atom and the field. So the quantum description of the interaction between the atom and the field will be proportional to this h cross xi, which is coming from here, which is scaling this interaction term, which is the product of the dipole moment and the electric intensity, which we know is proportional to the Rabi frequency. That is how we define the Rabi frequency, right? So it is this h cross xi, and now you have got the destruction and the creation operator for the photon and the lowering and the raising operator for the atom. So writing this quantizes the interaction. And now you have got a complete quantum description of the interaction between the atom and the radiation field, a single mode radiation field which is described by one photon. Okay? So you have this interaction. This is the cavity volume which you can decrease to make this electric field of the photon large, right? And this is the atom field quantum second quantized operator. Now notice, if you look at these four terms, so from the product of these two and these two you get four terms, okay? And let us look at these four terms carefully. Two of these are underscored by this green arc, the inner two, and the outer two are underscored by the red arc, and they have different properties. So look at those underscored by the green arc. So you have got a lowering operator here and the creation of a photon. So this is something that we sort of intuitively expect. In the other one, you have got the destruction of a photon and the raising of the atomic system, which is also we intuitively expect. But if you look at the other two terms, the F dagger R plus, what are you doing? You are raising the atomic system and you are also creating a photon. And look at the first term, which is also underscored by the red arc, which is Fr minus. You are destroying a photon and you are also lowering the state of the atomic system, R minus. So it would seem that the first and the last term underscored by the red arcs do not conserve energy, and they are sort of perplexing terms, but they are there. They have come through our process of second quantization, so they cannot be dismissed. Whereas the inner two terms, which are underscored by the green arcs, they conserve energy, they are intuitively appealing, and we feel comfortable with those, but the other two are also there. Okay? So these energy conserving terms are called as on the shell, and those which do not conserve energy are called as off shell, and off shell terms cannot induce real transitions, they will not even conserve energy, all right, but they can shift the spectra. Okay, they can shift the spectra to virtual states, and this is what is involved in the lamp shift. Okay. So in the previous course on quantum mechanics and the theory of atomic collisions and spectroscopy, I did relativistic quantum mechanics, I did the Dirac equation, and the solutions of the Dirac equation do not account for the lamp shift. Okay? The lamp shift is outside the Dirac model, and it is coming from here, because the atom can actually interact with vacuum, all right, and you cannot have a full transition, but the spectra can be lifted. So, that is the lamp shift, and this is the fully quantum electrodynamic Hamiltonian, which describes the two-level system interacting with the electromagnetic field. Okay, it's amazing. It's really the complete QED Hamiltonian. And let us just take one particular case, that if these 4 operators, they operate on G0. What is G0? The atom is in the ground state and there is no photon in the cavity. Okay? So, it is G comma 0. So, this is like a direct product state, okay, or a tensor product as it is sometimes called. It is a direct product of the atomic ground state and the vacuum state of the electromagnetic field. Okay? So, this is G0, and if the 4 operators operate on this, then 3 of these would give you 0, because you cannot lower the atom to anything lower than its lowest ground state. It is just a two-level system and it will simply kill that state. Okay? Similarly, when there is no photon in the state, you cannot destroy it. So, that would also give you a 0. The only thing which will give you non-zero contribution is what will give you the lamp shift. Okay? So, that will give you the lamp shift. It will not induce a transition from the ground state to an upper state, but the spectra will be displaced through the lamp shift. So, in the Dirac equation, the eigenvalues depend on the J quantum number. So, the J quantum number for the 2s half and the 2p half, both are J equal to half. But then there is a lamp shift over here which pulls down the 2p half compared to the 2s half. So, there is a spin orbit splitting between 2p half and 2p 3 half, but the 2p 1 half is not at this level, it is slightly lower down through about 4.372 10 to the minus 6 electron volts. This is the lamp shift for which Lamb got the Nobel Prize in 1955. Okay? So, these are now the 4 operators that you have with you. Okay? We will now consider the Dirac interaction picture, which you are familiar with, and the operators are now time dependent, okay, through this time dependence, as you know, right. This is the adjoint creation operator, and the raising and the lowering operators are also time dependent, but here you have the energy of the photon, here you have got the energy difference between the excited state and the ground state of the atom. So, there are 2 energies that you have, W and WA. W is the energy of the photon in units of h cross, WA is the atomic energy in units of h cross. Okay. So, now in the interaction picture, this atom field interaction is now written with all of these operators written as time dependent interaction picture operators. Okay. And now the time evolution, again this is something which I have discussed in some details in an earlier course, so I will not repeat it here, but you will find it on the internet on the special topics in the theory of atomic collisions and spectroscopy. It is in unit 4 of this, and in particular I will like to refer you to the slide number 41 in this, in which the time evolution is described by the Dyson operator, okay, which I have written the first few terms. It is actually an infinite series, and you have these integrals involved in the Dyson operator, and when you carry out this integration, you can notice immediately that you have got terms such as these which will be involved in the integrands, and that will give you terms like zeta over omega plus omega a. Forget about what is zeta, because it is just whatever comes in the numerator, which I have indicated as zeta. What is of importance are the terms in the denominator, the omega plus omega a and the omega minus omega a. So, what is going to happen at resonance, the omega and omega a will be nearly equal and they will dominate because the denominator goes to 0. Okay? And the other one, you will have 1 over twice the energy of a photon which is involved, and those will become ignorable. So, you can now carry out a certain approximation. You ignore the terms where you have omega plus omega a in the denominator, and you retain the terms where you have the difference between the two energies in the denominator. So, this is obviously an approximation, okay? And these are just the terms which are what you are ignoring are the off shell terms, what you are retaining are the on shell terms. Okay? So, this is what is called as a rotating wave approximation. This is just what we did semi classically by thinking about those two circles. We resolved linearly polarized light into rotating fields, all right. And then in the rotating field, one would go along with the Larmor precision and the other would be rotating in the opposite direction at twice the frequency, right. So, it is the same approximation which is known as the rotating wave approximation. It is the same physics which is coming over here, but it is formally justified in the second quantized QED formulation in the Dirac interaction picture. So, now we are working with a single mode excitation in the cavity. So, you have got the Rabi frequency, it is called as the vacuum Rabi frequency. It is sometimes also called as a 1 photon frequency. Why vacuum? Because when the atom is in the excited state, there is no photon anywhere. Okay? Whereas, if the atom is in the ground state, there is 1 photon over there. All right? So, you can either call it as vacuum Rabi frequency or 1 photon Rabi frequency. Okay? Both are completely equivalent and both the expressions are in use. And then when you make use of the rotating wave approximation, the quantum rotating wave approximation, you then ignore those two off shell terms, retain only the on shell terms. And now out of the 4 operators, you now have, out of the 4 terms, you have only 2 terms. The other 2 are ignored in the rotating wave approximation. Okay? But they are the ones what you are ignoring is they are physical terms. They are there because they should be there and they have a physical effect. They are the ones which lead to the Lamb shift. Okay? So, these are the ones which sort of conserve energy, these are the on shell terms, but then the only transitions which are involved are those which take you from the state En to Gn plus 1 and back. Okay. So, now you can have in the radiation field any number of photons, 1, 2, 3, 4 and so on. But the only transitions which are possible are between neighboring Fock states, n and n plus 1, nothing else. Okay? So, the whole Hilbert-Fock space sort of gets partitioned into pairs. in which the number of photons differs by just 1. The atom is in the ground state with n plus 1 photon, or it can be in an excited state with 1 photon less, which is n photons, and n can be 0. Okay? So, it is in such pairs that you will have the eigenvalue spectrum. So, we have introduced these quadrature operators earlier. I would like to remind you of some of their properties over here. Their expectation values in the occupation number states will be 0, okay, because they are sum of creation and destruction operators. So, they will reduce the occupation number, which will then be orthogonal to the previous occupation number state, or it will increase the occupation number, which will again be orthogonal to the previous occupation number state. But the squares are not 0. Okay? So, the expectation value of the square is half 2n plus 1, as you can see very easily by working out the expectation value of q square, all right, and that of p square is also exactly the same. So, both the expectation value of q square and p square are exactly the same, and now you can determine the uncertainties in the two quadratures. Okay, this is the generalized uncertainty principle, which we have studied long back when we introduced quantization, and the uncertainties in the two quadratures are essentially equal. We know from the uncertainty principle that the product of the uncertainties must be greater than or equal to 1/4 of the modulus square of the expectation value of the commutator of the two operators, right. So, now let us determine this for q and p, and since q and p is of modulus 1, the product of these uncertainties is greater than or equal to 1/4, right. And the expectation value of the squares of these operators is 1/2. That we have seen, which means that for n equal to 0 state, you will have this in the minimum uncertainty state. Okay? Uncertainty product has to be greater than or equal to 1/4, and you are already having half contribution from the expectation value of q square and the expectation value of p square in vacuum, right, to be given by half, the product of which is equal to 1/4. So, you cannot go anywhere less than that. So, essentially you are having the minimum uncertainty states. It is, however, possible to squeeze one of these at the cost of the other, okay, because it is a product which has to be minimum 1/4. So, you can squeeze one of these to be less than half, either of these, it does not matter, and then you get what are known as quantum squeezed states, and these are of great importance in quantum optics. But I will return to the primary discussion on the Jaynes-Cummings Hamiltonian, which is now in the rotating wave approximation. Out of the 4 terms, the off-shell terms are now ignored, and you are left with the 2 on-shell terms in the Jaynes-Cummings model. So, this is the Jaynes-Cummings Hamiltonian. It is a complete quantum electrodynamical Hamiltonian, except for the fact that the off-shell terms are ignored. Okay? So, here is a picture of the energy level diagram. So, you can have n photons in this state and n plus 1 photons in this state. The energy difference between the atom's excited state and the ground state, which is h cross omega a, may or may not be equal to this. It will be equal to that only at resonance, otherwise it will be away from resonance, right. So, delta is the detuning parameter, which is the energy difference omega A minus omega, but it can also be the other way around. So, delta can be positive or negative, it depends on which side of the resonance you are. Okay. So, here I have shown delta to be positive, but it can be negative of course. So, this is the energy level diagram. This is the non-resonant situation because the two energies are obviously different. The atomic states are eigenstates of H0, and you have these two states. So, you have got the n plus 1 photon state over here, so whose energy will be h cross omega times n plus 1, but it will be half delta h cross above that and half h cross times delta below that, right. So, this is the pair of states which represent the states, energy states of the system, and now you have got a two-dimensional Hilbert space or a Hilbert-Fock space if you like. So, depending on the number of photons, you may have many levels, and you will have those levels. I am going to show you another energy level diagram in which you have all of these energy level diagrams. But that complete energy level diagram sort of partitions into such pairs, because the only transitions which are now possible under the Jaynes-Cummings Hamiltonian, which has got those two terms which can only induce upward or downward transitions which differ by one photon. That is the only thing that is possible. So, only these two states, which is G n plus 1 and E n, but n can be anything, n can be 0, n can be 1, n can be 2, n can be 3 and so on, right. But the whole Hilbert-Fock space partitions into such two-dimensional space which I have indicated by sigma n, where n is the number of photons when the atom is in the excited state. So, this is just for bookkeeping purpose, that this two-dimensional Hilbert space is denoted by this sigma n, where n is the number of photons when the atom is in the excited state. So, this is one number less than what it would be if the atom would be in the ground state. So, at resonance, if you look at these energy eigenvalues, they become equal when delta is 0. Delta is the detuning. At resonance, they would become degenerate, but we have written this in product states, in tensor product states. The electromagnetic field interaction with the atom will remove this degeneracy. Okay, there is that interaction. So, here this is written in factor states. Okay. So, at resonance, this will be lifted. Under non-resonant conditions, delta is not 0, so there is detuning, omega is not equal to omega A, these are not degenerate, and the atom is in the excited state with n photons, or the atom can be in the ground state with n plus 1 photons, as I pointed out earlier. So, these are the two states that we have to remember, and the energy eigenvalues I denote here with these subscripts E comma n and G comma n plus 1. So, it is either E comma n or G comma n plus 1, and those are the two factor states in which the atom radiation field can reside. So, good. So, notice that the interaction Hamiltonian commutes with the sum of the atomic Hamiltonian and the Hamiltonian for the electromagnetic field, and the Jaynes-Cummings Hamiltonian, which is just the two terms, also commutes with this, all right. The Jaynes-Cummings Hamiltonian interacts with the atomic Hamiltonian, and this is what happens at resonance. So, H0 if I write as a sum of the atomic Hamiltonian and the field Hamiltonian, then it commutes with the interaction Hamiltonian. So, at the resonance energy, these omegas are equal. This is the angular frequency of the photon, and this is the energy difference between the excited state and the ground state of the atom, which is omega A. So, omega A becomes equal to omega at resonance, and you can then extract this H cross omega as common between the atomic Hamiltonian and the field Hamiltonian. It comes out as common, which is H cross omega A, and you can write the sum of the two operators like this. Okay. So, this is your Jaynes Cummings Hamiltonian. This is the part corresponding to the atom and the field, and this is the part corresponding to the atom field interaction. So, we define an operator which is n, which is the sum of this number operator for the field and a similar operator for the raising and lowering operators for the atomic excitation and de-excitation. Okay? And notice that this operator will have to be proportional to the atomic and field Hamiltonian H0. Okay? So, this is, since the Jaynes Cummings Hamiltonian commutes with n, it also commutes with H0, and H0 and n will then be proportional, the proportionality being the energy of the atom, which is the difference in the energy between the excited state and the ground state. So, this is the total number of excitation quanta is conserved, because the energy is either in the atom or in the field. It cannot be in both. So, this is the larger picture as I mentioned. So, you have got these states which have different number of field quanta. So, you can have 1 photon states, you can have 0 photon state at the bottom, then you have got the 1 photon state over here, you can have the 2 photon state, and then the multi photon state like n plus 1 photon states, and the energy difference will be a certain integer multiple of H cross omega, and then between every pair the difference will be exactly H cross omega. From 1 photon to the second photon it will be H cross omega, from the 2 photon to the 3 photon it will be exactly H cross omega, and then around that you will have these pairs of levels, okay, which are denoted by sigma and the number of photons when the atom is in the excited state. So, sigma 0 is this state, and the number of photon when the atom is in the ground state is 1. The difference is H cross delta, well delta is the detuning. Okay. Over here there will be only one state. For the 0 photon state there is only one, but everything else will have pairs, because right. So, you have got this energy level diagram. You know what these energies are. The eigenvalues of H0, H0 is the sum of the Hamiltonian for the atom and the field. So, that is this H cross omega n plus 1 for the excited state raised through half delta in units of H cross, and this is lower by half delta. So, the difference is H cross delta between these two states. Okay. So, you have got these pairs, and the whole Hilbert-Fock space is now partitioned into these pairs, and the Jaynes Cummings Hamiltonian just has to work with one pair at a time. Okay. So, the n equal to 0 state is uncoupled, and every 2 level manifold. So, every pair is a manifold, every 2 level manifold is separated from the neighboring one by 1 photon energy, which is the single mode cavity energy. Okay. These are the bare levels. They are the levels of the factor states, okay? But the interaction is going to dress them up. So, you will have the dressed states, which is what we have to determine, and that will happen because this Hamiltonian will not be diagonal in this basis, and you will have to diagonalize it. So, here these are the eigenvalues of the unentangled states. The atom and the radiation field have not generated entangled states at this point. These are unentangled factor states, and when delta is not 0, I already mentioned that they are not degenerate, but then when delta is 0, there will be resonance that suggests that they may be degenerate, but the degeneracy is going to be lifted by this interaction, which gets switched on at resonance. Okay? It is the resonance condition under which this interaction is switched on and the degeneracy will be lifted. So, this is your atom field interaction term. We know the matrix elements of the creation and destruction operators. So, you can find the matrix element of the interaction Hamiltonian between the occupation number states. And because you know that you have got the square root n and square root n plus 1 factors, you can immediately find the absorption probability amplitude and the emission probability amplitude, and it comes as a no surprise that they are exactly equal to h cross xi square root of n plus 1. But remember that this depends on n. So, if there are 2 photons in the cavity, then this probability amplitude is higher than what it would be if there was only 1 photon, and that would be higher if there was no photon. And if there are 10 photons, then there will be square root of 10 plus 1. So, that scaling will be done by square root of n plus 1, and this is the term coming in the transition probability amplitude, which we had defined in such a way that the Rabi frequency was proportional to that. So, the Rabi frequency will also get scaled by square root of n plus 1 depending on the number of photons in the cavity. Okay. So, only this 2-dimensional Hilbert manifold is involved now, alright, but the number of photons can be either 0, 1, 2, 3 or many, and the 2 transition probability amplitudes are exactly equal, and this is a very powerful reduction of the fully quantum electrodynamical manifestation of the atom light interaction. So, you have got a full QED Hamiltonian. Okay? There is only one thing we have done, which is the rotating wave approximation, and we have ignored the off-shell terms. We know that they are not going to change the physics. The only thing they will do is to contribute to the lamp shift and change the level of the spectrum. Okay? But the physics is not going to be affected by this. So, this is the Jaynes-Cummings Hamiltonian, and we will discuss it in the next class. This is all the 4 terms that we had in quantizing the semi-classical Hamiltonian. 2 of these are ignored in the rotating wave approximation. In the semi-classical model also we did a similar thing, but at that time we considered the resolution of linearly polarized light in 2 rotating polarized, one clockwise and the other anti-clockwise, and we ignored one of these. And in this case we went over to the Dirac interaction picture, and from the solution to the Dyson equation we recognize that some terms will have 1 over difference in the energies. Those are the terms that we retained. Those are the on-shell terms. So, thank you very much. We will continue from here in the next class. If there is any question, I will be happy to take it.
Sir, in that levels we have that for like 2 levels which the distance between them is like single photon. Will there be any transition from one set of states to another set of states?
Yes.
Okay, like for example, if I have a transition from like 3 photon state to a single photon state.
No, no. That is not a part of this. Okay? You are talking only about 2 levels at a time. So, this is a single photon transition. Okay, so thank you very much.